The first thing we need to talk about here are tangent lines. Usually you discuss tangent lines in the context of circles. And a tangent line, in that case, is a line that just grazes the circle in one point. Well, we have to be a little bit more general than that. We're going to be talking about arbitrary graphs, in which case our tangent lines still look like they graze here, but they don't necessarily hit in just one place, because if I follow one of these tangent lines, it might hit the graph in another place. But the key thing is, if you look around this particular graph right here, we're going to see that a tangent line is the line that in that little region right there looks most like the graph. Or in this little region, it looks more like the graph. The way I like to think about this is, if I draw a small circle around the point I'm interested in, the red line and the blue curve are going to be almost indistinguishable. If the graph is really curved, like it is right here, you will see a little bit of a difference. But look at this other part where it's a little bit straighter. The tangent line and the blue curve look almost exactly alike. Now, a secant line is something a little bit different. A secant line is a line that passes through 2 points on the curve. In this case, I've put a point labeled A, and there's the point on the curve. And I've got another one that's some distance h away, and it's at a position A plus h, and I've got a point on the curve there. It's not a mystical reason why I used A and A plus h, and in the previous section we used A and A plus h, because these things are going to start to look alike. So if we want to find the slope of this secant line, all I have to do is look at the different values here. So at A, the value of the function is f of A, and at A plus h, the value of the function is going to be f of A plus h. So if I want to know the rise in this, I'm going to want to know the difference between f of A plus h and f of A. So I'm going to go ahead and subtract them. The run is simply going to be the difference between these x values down here. And so if I take A plus h and subtract A, of course, I get h, because I told you that they were h apart. The rise here is the difference between the y values, and that's why we say f of A plus h minus f of A, because remember, f gives me y values. And the difference in the x values here is just h. Look at that quotient that I just came up here. Isn't that the exact same quotient that we used when we talked about average rate of change? It's the exact same thing, except now instead of talking about average rate of change, I'm talking about the slope of a secant line. What happens to this line if I make the distance h here smaller and smaller? Well, if the distance h gets smaller and smaller, this point is going to start to migrate up towards the other one. Notice as it migrates up, the secant line starts to change a little bit until eventually it gets very, very close and it looks exactly like the tangent line. As the 2 points get closer and closer together, the secant line gets closer and closer to the tangent line. So in a sense, secant lines, if the points are very close together, look pretty much like tangent lines. We've been approximating the slope of the tangent line by finding the slope of the secant line through 2 points. By moving one point closer to the other, we can discern the pattern of the slopes in the secant line and then say that is the slope of the tangent line. The reason why we just can't directly do the slope of the tangent line is because we can't pick 2 points on the curve that go through the tangent. The tangent only touches at one place, so we can't do the same thing that we did before. But what's nice is this idea can be expressed as a limit. The tangent line of the graph of the function y equals f of x at the point a f of a is a line through that point having the slope f of A plus h minus f of A over h, the limit as h approaches 0. So this difference quotient here was just our slope of our secant line. By saying h is approaching 0, we're going to let the points get very, very close together, in fact, infinitesimally close, and the pattern that we get out of that is going to give us the slope of the tangent line. We can do this as long as the limit exists. If the limit does not exist, then we'd say that there isn't a tangent at that point, and a little later on we'll see some examples of that. Let's go ahead and find the slope of the tangent line to f of x equals x squared plus 2x at the point x equals 1. We're going to basically do exactly like we did in the previous section. The only difference now is instead of calling things instantaneous rate of change, we're just going to say slope of the tangent line. We need to use the definition of the slope of the tangent line with a equals 1, so we're going to do the limit as h approaches 0 of f of 1 plus h minus f of 1 over h. This is exactly what we did in the previous section, except there we would have said it was the instantaneous rate of change at 1. But now, because we're doing this geometric, it's all the slope of the tangent line. So let's go ahead and find each one of these pieces. We're going to subtract them, divide by h, and then do the limit. So first of all, f of 1. Well, if we put 1 into this function, we get 1 squared plus 2 times 1. That's 3. If we do f of 1 plus h, that means we need to put 1 plus h in place of x. So we get 1 plus h squared from the x squared, 2 times the quantity 1 plus h instead of 2x. And now, just as we've done before, we're going to go ahead and FOIL that out and simplify all of this. So when we take 1 plus h times 1 plus h, we get 1 plus 2h plus h squared. 2 times 1 plus h gives us 2 plus 2h. I see some like terms here that we can combine together. So when we do that, we see the 1 and the 2 become 3, the 2h and the 2h become 4h, and the h squared comes along from the right because there wasn't a like term for that one. We'll go ahead and take our definition that we wrote down before, and we're going to go ahead and put in f of 1 plus h, which was 3 plus 4h plus h squared, and subtract f of 1, which was 3. To do this limit, we could go ahead and just try and plug in h equals 0, but the top part would be 0 and the bottom part would be 0. And that's typically a signal that we're going to have to go ahead and do some reducing here and try and cancel out that h before we take our limit. I'm going to go ahead and cancel out the 3's, and I'm left with 4h plus h squared. Like our previous examples, we can factor an h out of that, and then that can cancel with the denominator. So we'll go ahead and do that canceling. What we're left with is 4 plus h, and as h gets very small, h is going to approach 0. There's no h in the other term, so the limit as h approaches 0 of 4 plus h is just 4. So that tells me that the slope of the tangent line on this parabola at x equals 1 is a slope of 4. Here I've gone ahead and drawn that tangent line on there. And if you look at it really carefully, we go over 1, up 1, 2, 3, 4. That's certainly a slope of 4. That tangent line passes through the point 1, 3 because f of 1 is equal to 3. So if we wanted to find the equation of that line, which is how I put it on that graph, we'd start from our point slope form, which is y minus y1 equals the slope times the quantity x minus x1, where x1 and y1 is our point that we have up here. And the slope in this case is the slope of the tangent line that we just found up here. So all I need to do is plug those values in here, and I'll have the equation of that line that was on the previous graph. So I'll go ahead and put the 3 in place of y1, the 1 in place of x1, and the 4 in place of the slope of the tangent line. If I go ahead and add 3 to both sides, I get y equals 4 times the quantity x minus 1 plus 3. And then I can go ahead and distribute, combine my like terms, and what I get is y equals 4x minus 1. This is in slope-intercept form. When I just plugged the numbers in, that was still in point-slope form. Which one of the answers you supply depends on what you're asked for. But they're both the equation of the line. It's just it's in different forms.